Uh, Good morning, folks. Welcome to BAS's first Tech Talk of 2024. Uh, Most of you, I see a few new faces. So let me tell what BAS is about. BAS is a bunch of volunteers who got together a few years ago with a common interest of astronomy, spreading science, scientific knowledge, and the scientific temper to pretty much everybody that we can reach out to. We are a purely non-profit organization uh, run by run by volunteers. What does BAS do? We do outreach sessions in the field of astronomy. We conduct star parties every so often, especially in the winter months. We have one particular site that we go to, what we call a dark site, where we go and look at what others think is faint fuzzies. We derive a lot of pleasure out of it. Something that we truly enjoy. Uh, we we are since we are purely a volunteer run organization. We are always looking for volunteers, whether it is conducting tech talks like this, whether it is doing outreach programs. We Recently, I think a couple of months ago, we did an outreach program at Jain College. We're always looking out to do more outreach programs in other colleges, and I see a bunch of people from BMS College. We'd love to do such outreach programs. We need volunteers. We also need volunteers to spread the word in your network, in your college, in your WhatsApp groups, in your housing societies. If you can spread the word about astronomy, about BAS, will be very nice. Be really grateful to you, Shashi. So without much ado, let's get to the topic. Let's talk about today's topic. Okay. All right. Today's topic is titled Chandrayaan 3: Mapping the Journey from Sriharikota to Shiv Shakti Point. Uh, in August last year, you're all aware that ISRO launched the Chandrayaan 3. Uh, I distinctly remember. I was glued to the streaming from ISRO. The culmination was a landing of the spacecraft on moon surface, and then the rover rolling out. It was something uh, that it gave a lot of joy to a lot of people. We have Shankar with us today. So let me brief you about Shankar. Uh, I have a small note written down here. Shankar Narayan Vishwanathan, a multidimensional astronomy enthusiast, currently empowering Ola Electric Cloud Technologies, and a seasoned amateur astronomer for more than a decade. His orbital simulations were used by multiple news channels and have been featured in numerous blogs and articles. He is here now to talk about Chandrayaan 3, straight from the horse's mouth. So let's welcome Shankar, and let's hear what the entire Chandrayaan story straight from Shankar. Shankar, over to you.
All right. Thank you, Nandan. Thanks to Bangalore Astronomy Society for giving me this platform. So, what we're going to do today, is to talk about Chandrayaan 3, specifically the trajectory part, the orbit part, right? So, we all know how do we map things on ground. We all use Google Maps, correct, to go from point A to point B. Now, what if you were to plot the same track from Sriharikota, the launch pad, to Shiv Shakti Point, which was named after it landed, soft landed, right? How do we even do that? How do we start imagining doing that, and how do we get there, right? So that's the crux of this talk, right? So what we will do is, uh, it's focused on the the space and geometry of the trajectory. We will answer common questions which many people have, like what was the path taken, why does it go round and down, why not straight, right? Why it takes 40 days to reach? Isn't there a faster orbit? Um, why those spiral orbits? Why revolve so many times, right? So we will be using only foundational principles, whatever you have learned in at most in plus two. Very little math, uh, maybe high school physics, but more intuitive, right? More intuition, more geometry, right? That's what we'll use, right? And we will heavily use a lot of visualize, not just my animation, but there are several platforms uh, on the net which you can use, right? There are several tools you will see, and you will see, how to make use of it for a better learning. We will appreciate the constraints involved by the design team at ISRO, what they faced and how they, navigated that, and eventually, ultimately, ignite more curiosity. That's what it did, right? When it got launched, and when it landed, right? That's the goal, right? What this is not a crash course. This is just a small 1.5 to 2 hour session. So not really a, you know, I can't teach you astrodynamics. I don't know at all, right? Not rocket science. Not seriously into, we're not at all talking about any science payloads or research which went on the 14 days after it landed. Not that, right? This is mainly about space, geometry, orbits. Uh, that's the crux of the talk, right? Hope that interests you, right? So what we want to do, right? It's like, something like this, right? We have the known, we have the unknown. So we want to basically increase little bit your uh, known circle a little bit, and then the known unknowns, right? Which you didn't know that you had in known that quite a bit. That's the aim of this talk, right? So that's what we are headed to. Okay, bottom you have pen and silver. Yeah, yeah, yeah. It should have come even otherwise. I guess, yeah, it is there. There you are. All right. So this is an online session. So I think one of the moderators will be taking questions coming over chat. There'll be quizzes, online quizzes. So maybe 5 quizzes just to keep your interest, levels high. You can raise chat to raise the questions, and we will pick it up after every segment. So we have different segments up here. So this is the Q's site website. Hope you can scan it and see if you can log in. And once you log in, we will do a quick quiz just to check whether you are able to access it. All right. Or you can enter the code directly, right? Capital H C small W 4. Just 4 letters. Sorry. Yep. Let's start the poll, right? So that's the poll. So the first question is coming up. Look at this picture, right? What's it? No, you have to answer the answer in the platform. All right. Just to get to warm you up, right? So you can see, answers coming up. It's they are not in the order in which you see the options arranged. Uh, Kansas City. Can you keep the QR code on? QR code on? Yeah, sure. Uh, uh, oh yeah, in the presentation. Yes, I think that's here. So we have 7 answers. You can also copy paste the link to the chat, right? Yeah. All right, that this is warm up. So we all know that was the observation gallery in the launch facility, right? So what's our outline going to be today? So it's primarily 2 sections. So initially there will be a foundational section where we will go over the scale, the coordinate systems which are used in astronomy. Right? Our goal is to map the trajectory. So if you want to map it, you should know about the scale which you're talking about, right? We should have a coordinate system. and we have two objects involved, Earth and Moon. Earth, we all know how it's mapped. So now we're going to map the Moon. How do we do that? We'll get to the trajectory part, and then we'll analyze the trajectory and see its structures in terms of orbits. Then we look at maneuvers, how we can alter the course of orbit. Then we will get into mission design, right? So how was this mission design? What are the constraints? What are the factors? So we'll go backwards and derive for ourselves, how the trajectory is designed, right? So we'll start from the lunar orbits of Chandrayaan 3, then go work backwards, then to the transfer orbit from Earth to Moon, and then finally the launch orbit, right? And overall see how this is achieved, right? That's a rough outline. So we'll start with scale, right? So scale, this is a map, and every map is drawn to a scale, right? So this is shows trajectory from Bangalore to Sriharikota, right? And to Shiv Shakti point, we don't know. That's what we are going to do now, right? So this is a map, and it has a specific scale, 344 kilometers mapped to this width of the screen, roughly, right? So this is a map. So do we have a map for the Chandrayaan trajectory? Yes, we do have, but is it to scale? When I see this, I get a lot of questions, right, for myself. Are the Moon and Earth to scale? Are the orbits to scale? And why is it that uh, why is it that this orbit here, okay, uh, on the Moon's orbit, right? Why is it tilted in this way? There is a let me just mark it. Okay, why is it tilted in this way? This is drawn in this way, and this is tilted in this way. Why is that, right? Um, and then why these 5 layers up here, 5 layers up here? Is it that the spacecraft took one orbit each in each of those 5, or is it that it took more? Um, and what really is the scale, right? These are questions which you want to answer, right? Uh, be curious and get to know what is there. And there is a final moon landing uh, orbit here, how it deboosted and landed on the moon, right? So how do we get there, correct? So now what we want to do is move forward and see, did ISRO share really details about the orbit in more detail than the schematic sketch? They didn't. They shared a lot of very informative stuff on social media. These are some of the screenshots they kept sharing to keep the interest level up. Uh, and you can always see that it's always schematic, right? It's not get into more depth, which some people may want to know about, right? So now how do we start? Okay, so what they did was sharing a schematic. This is a Bangalore metro map. On the left is a realistic map to scale with places annotated. On the right is a schematic. Correct. No places marked, only stations marked. Roughly, directions are rough, not exactly the same, right? If you want to go beyond the schematic, the first step to do that is to figure out the scale, the size of Earth and Moon. Okay. So now, we have a little experiment. I want 2 volunteers, all right, to come over here and then tell me, pick 3, globes, balls from the on the table, uh, which can represent maybe sun, earth, and moon. Can a couple of you come over? Obvious? All right. Yep. There you are. So I wanted to pick up, balls representing the relative sizes of, let's say, sun, earth, and moon. If it's not possible, let me know. Then I will modify the problem. But otherwise, pick any 3 balls: sun, earth, and moon. Okay. So we are looking for scale. Okay. So what that means is they must be in proportion, right? All right. Okay. What about the moon? Any other answers from the audience? Who wants to try? So by this choice, Sun is only about 2 or 3 times in diameter compared to Earth. Yeah, it's huge, right? And what about the moon? Is it? It's probably about the balls which you picked, right? It's probably uh, 2/3 the size. Hmm? Is that the case? We'll find out. Thanks for coming over. Let's give them a hand. All right. So in reality, right? So among the balls kept, okay, there is a. Let me switch to the slide deck again. Control Alt 1. All right. Okay, switch back. So it turns out, or maybe I will just go there for a second, right? And so it turns out that sun, obviously, you cannot. There's no representation here for sun. Whatever you pick as Earth, it's so huge. There is no ball representing sun. Okay. Then the next best we can do is probably pick Earth and Moon. So Moon is just about 1/4 in radius compared to Earth. So the right answer is this ball and this small marble. Okay, not this, you know, nor this, or even if you take, there's nothing sort of matches the ratios, right? So that's the first thing you should realize, that it's just 1/4 in radius or diameter, right? That means in volume it's 64 times higher. So that's the scale you're talking about. What about the distance? What should be the distance between these two? Okay, anybody wants to come and tell me? Pick these two. Okay, let me keep them here. What about the distance? Are they this far apart? This far? This far? Any guesses? So I need 3 volunteers. All right. Please come. So I need one more. Hold this. Uh, we are going to hold this side by side. Align with this edge on edge, and you're going to stand there. All right, and you're going to stand there, right? In line, in a plane, in a plane. So now that's the distance you're talking about. This is Earth. This is Earth. Okay, it's about 6 centimeters in scale here, and you got to have 60, 30 Earths, 30 such balls placed, and then you get to the moon. Okay, so in reality, this is about 6,400 kilometers in radius. This is about 1,700, about 1/4, and this distance is 384,400 kilometers. Right, that's the scale. So we all miss the scale when we see schematics. So the idea was to just give you a sense of scale, so that what exactly are you talking about, right? And if this is Earth, right, the low Earth orbit satellites, they are extremely close. They're on a tight loop around Earth. So including ISS, which is at 400 kilometers, right? That's how they rotate. So there is a long way to go to the moon, all right? So if you take GEO, right, they are about 36,000 kilometers, about probably up here, right? GPS probably up here, correct? So they have all the way to go. How do we go? That's the whole point of this talk. Hey, thanks. Give them a hand. Now that we have a sense of scale, okay, let's switch back. Okay, that's the answer, right? So this is the scale which you talked about. Okay, 6,400 roughly, um, 384K, 30 Hertz, 1/4 radius, right? This again, what we said about the same showing orbits for scale. You can also see that the moon, right? Let me add something up here. Oh, not there. Okay. It shows about 1 light second to reach the moon. It shows relative sizes, right? So now let's move. If you plot it on, if you scale it down and plot it on a map uh, for comparison, right? So on the north, I picked up Hubli, right, and Bangalore is the distance, so about 384 kilometers. So I just scale it down 1:1,000. Okay, and then Earth would be about 6 kilometer radius in Bangalore and Moon 1.7 kilometer in Hubli, right? That's the kind of scale, right? So now you've got a sense of scale, right? We need to see what coordinate systems can we use to map. Ultimately, our goal is to map, right? So we're all familiar with coordinate systems on Earth. We use latitude, longitude. On a graphing sheet, we all use X and Y, right? So something similar we need, right? So we need in 3D, right? We need X, Y, Z. We are all familiar with that, all learned in school. So either we can use X, Y, Z, or we can use R, theta, and phi, right? A radius, and then you can use uh, an angle, a couple of angles, right? So we're going to see, how do we? Let's try this out. Okay, let's try this out on how to use that, right? So we have this demo up here. Hope you can see that. So here I can see this x-axis. Okay, uh, y-axis. Let's see the y-axis. Probably not here. I can see from the top, or I can see from the side, right? Or I can see from the oblique view. So y is up here on this line, and you can see that there is an angle called right ascension. This one angle, another angle called declination, and of course there is a star which is mapped, right? So that's r, theta, and phi. So we always use something similar, right, in mapping 3D stuff. So you can also use another site here which says plots the same. Okay, let me get there up here, right? So I can change it. This I'm changing the right ascension. So for hours 60 degrees, and if I change the declination, right, uh, adjusting this, you can see that it goes all the way to the north, uh, or on the equator, or can go south. I can adjust it, right? Together with the radial distance will give me where that is placed. But now the question is, what is this x, y, z? Who defines it? We all have to agree that this is the same x and y we are referring to, right? So, so there is such a xy plane. In astronomy, we are all familiar with the equatorial plane, the the plane defined by the equator of the Earth, right? And we are familiar with the North Pole, right? You use the right-hand thumb screw rule, and then you get the North Pole, right? So that's a fundamental plane. It can be easily be measured. It has been measured in various ways since the very beginnings of astronomy. And there is another plane, which is the ecliptic plane, which is by which the Earth revolves around the sun, right? We have two fundamental planes, and it turns out that as you can see on the on the globe, right, Earth's axis is tilted to the plane in which it rotates around the sun, and they both intersect, right? So if they both intersect, right, you can see up here ecliptic and sun, they intercept, right? This ecliptic is the pink line, and the equator is the blue line. They intercept, right? And wherever the ecliptic crosses, the cuts the equator and goes towards the north. That point we define it as that is x-axis. Okay. So we have a first point of Aries, or the vernal equinox point, that we define it as x-axis, right? 90 degrees on the ecliptic plane we can choose as the y-axis, and the z-axis pointing to the ecliptic north pole, right? So you define x, y, z. That's it. We all agree that that's the coordinate system and use it, right? There have been different ways in which these planes have been realized. Uh, Either you can go with equatorial plane, okay, or you can go with ecliptic plane as xy plane. You can see both in astronomy, right? And there are phenomena by which these planes are not really uh, inertial in the sense they are not they precess, or they like a spinning top, it precesses, right? But then we say that at a specific instant we can always say that, hey, I will choose xyz to be aligned with the these coordinates or the first point of varies on a specific date. Then we all align, correct? We can say that on whatever the planes are on January 2000, January 1st 2000 0 hours, that's my epoch, and on that I align, right? So that's what astronomers have done. So they all agree that they choose something like beginning of 2000 as the epoch, and they pick the intersecting points between these planes, agree that is xy plane, and then then you can map it. It's easy to map. We have an agreement on what everybody refers to.
Here, which is the X and which is the Y?
Yes. So the X is what you see, where the ecliptic goes from south to north, right? This is the north, right? This is the north, which pointing I'm pointing to. And from south to north, it cuts the, equator and then goes up, right? This is the first point of Aries, or the X axis. And in a right-handed system, right, the Y points, if you are using ecliptic as xy plane, it points here, up here, right? The peak point, that the 90-degree point, that is a Y, and Z is the ecliptic north. But if you are going with equator as xy plane, then obviously the point where 6 hours right ascension, right, that is a 90-degree point, right? That happens to be the y-axis, all right? So we have an agreement that we all agree that, hey, I will use this reference plane, equatorial coordinates at year 2000 epoch, right? Then we have an agreement between astronomers and everybody that we can then plot, right? Then we can communicate, hey, these are the coordinates measured in that coordinate system, and we use that, right? So that is a way to achieve that. So these we need so that we can plot the plot whatever you want. We can plot the locations of sun, the planets, or even spacecraft. So right now, I've talked about the scale and how a basic coordinate system is defined in astronomy, right? So with that, we can get to the next step. Can we get to mapping Chandrayaan strategy, right? So this is again another view, through your question, right? So this is the vernal equinox. I can take y as the coordinate pointing 90 degrees in the right hand thumb screw on the ecliptic. Then z is the ecliptic north pole, right? And here you can see that the Earth's equator is tilted, right? 23 degrees, 23 and a half degrees. So typically in these diagrams, right, you may find these drawn in two different ways. Sometimes the ecliptic plane will be level to your eyes, like level to the ground on the Earth. That's how it's drawn. That's how everybody makes the globe. Okay, I wonder why. Why is it? Why they can just make it horizontal, right, to the eye level? It's easier to look at, and then tell everybody that, hey, ecliptic plane is 23 degrees inclined. But then they make it that way, right? So you will see both diagrams. Uh, you have to get used to that, okay? But you have to know where what we are referring to, because the vernal equinox is where uh, the ecliptic goes process from south to north, right? So here you can see. Let me take this up. I think that so it is. Yeah, you can see that this way. Then, okay, it is going up, right? So that's why this is X. Okay. Uh, Ecliptic plane goes towards the north, right? So these are, coordinates. If you take ecliptic plane, we refer to those angles as longitude and latitude. Longitude is measured across ecliptic and latitude measured, perpendicular to that. If you go with celestial equator, we call it right translation and declination, right? And this is a graphic from Wikipedia, which shows, how is it rendered. So it's an animation. You can see it's getting rendered, alpha and delta. Those are the two angles on the equatorial plane if you are going with the equator as xy plane. But if you choose ecliptic, it will render with longitude and latitude, right, to the same star, right? Lambda and beta, longitude and latitude. Usually, because we deal with only angles most of the time in astronomy, we don't specifically refer to the distance. But in the case of spacecraft trajectory, obviously we need to know about the distance, right? This shows that the galactic equator also, we don't have to worry about that. Okay, let's move on, right? Yes.
Usually measure this latitude longitude with respect to the equator. I mean, when we are coming to this globe.
Huh.
So what we will be using in this would be with respect to the ecliptic.
You can go with both. So the question is, usually we use equator. Um, um, in mapping spacecraft trajectory, do we go with that or do we go with ecliptic? Both can be used. Both can be used. So you can get coordinates wherever available they are available from in either form. So they can go with an equatorial reference frame or you can go with an ecliptic reference frame.
What reference frame?
So they could have used both. They could have used both. Yeah, we don't know internally what they could have used. They could have used multiple for various purposes. Uh, in plotting my animation, I use ecliptic coordinates.
Oh,
Okay, uh, because the ecliptic plane is quite fundamental, right? It's we want to know relative to the Earth's orbit. How is Moon's orbit aligned? One could have used any of them.
so technically, so from sun and the earth, so the plane that connects the sun and the earth.
Yes, exactly. Earth's orbit makes the ecliptic plane. Absolutely.
Sides.
Yes, on that plane, we need x and y, right? So we have a plane defined by Earth's revolution around Sun, and on that plane, we have to arbitrarily choose an x and a y, and this x is chosen to be pointing towards the vernal equinox, the point where the ecliptic crosses the equator and goes north, right? That's how they were defined. But in modern times, we have changed how things are measured. Nowadays we use, rather than relying on the dynamics of Earth, Moon, and Sun, which keep changing, we have better measures these days. So now we are looking at quasars, like 3C 273 in Virgo, brightest quasar, uh, which are very far off, millions of light years away, so that you really do not perceive any motion at all, and you can choose a bunch of such quasars as defining the frame, okay, as defining xyz. uh, and you don't have to rely on measuring the equatorial plane and ecliptic plane, which have a lot of perturbation. They don't have a constant motion. They are perturbed by phenomena on Earth, such as Earth slowing down in its rotation due to tidal effects, perturbations from other planets, precession, um, unknown things, right? So we don't have to worry about it. We have better, practical realization by defining these XYZ with quasars. But then we don't have to worry about that. For our session today, we just need to know that hey, there is an XYZ which you have to use, right? And regardless of how it's defined, we will just use it. Okay. Uh,
So one other question. All the measurements you do with respect to the sun, right?
it can be done again in different ways. So in in orbit planning, you can do related to the Earth, related to the Moon. Both have been done. So when you plan a trajectory, right, you will do both. You will do both because you eventually need to take care of effects of all the celestial bodies. Correct? It's not a two-body problem. It's a n-body problem, right? So and you would use coordinate transformations back and forth. So definitely for the CY3, both Earth and Moon based coordinate systems have been used. Okay, both inertial as well as rotating. For some calculations, you would have to pick in a rotating frame For example, if you're landing on the moon, uh, you got to land, right? You got to know how the surface rotates, right? So you will pick a convenient coordinate system which rotates with the moon. The Earth longitude and latitude rotates with the Earth. That's why Bangalore's longitude and latitude remain static, right? It doesn't keep changing with the rotation of the Earth, correct? It's always 13 degrees north, whatever, 77 degrees east, right? It's fixed. So that's a Earth fixed coordinate frame. Moon fixed coordinate frames exist. So moon fixed coordinate frames have been used for modeling the final descent, whereas Earth-based coordinate system have been designed for the initial orbit trajectories. Then when you go to the moon, once the craft enters the moon's sphere of influence, right, it's convenient to use moon coordinates, moon-based coordinates. All right. So you can play around. There are huh,
So this spherical coordinate system, how is it different from the RA deck system that we use for astronomy?
huh.
When I'm looking at a star, I tell this is my RA. This
Yeah, yeah.
How is
We
it?
just define, you get XYZ, right? So primarily either use XYZ or you can say R theta phi. And R is typically not used for stars because they're so distant and we don't care about R, right? They are so far, R doesn't change and they don't impact the theta and phi, right? They remain more or less the same. So you typically are okay with two angles,
Right, theta and phi.
theta and phi, right? So you can play around, right? You can understand these concepts better by sites like GeoGebra, right? So this is a great platform. You can GeoGebra and you can define equations in math. Render globes like this, and you can play around. For example, here there is a Earth's the fundamental planes are marked here, so right, and you can play around and see like I can point it so that I'm in the west. So the equator runs sort of at an angle like this, right? And I can start, how is the daily motion look like? The sun rises in the east, sets in the west. I can also set an annual motion, right? Um, in which case, I can increase it here in this example. So this site is a platform is pretty good. I would suggest explore this. It's a great educational tool to learn, to know and learn. There are people who have put very good astronomy animations on this platform. Okay, so GeoGebra, right? So now that we have got an understanding, let's move on, and now we'll move to how do you map the moon. Okay. So we all know how we map the Earth. So I'm not going to get into that. How do we map the moon? So this is the moon with all the craters labeled. All right, and typically these pictures, right, they render moon with its north point up. Okay, so this is the north. Okay, that is up. Let me just
How do we have the north actually? Is it based on the adaptation and mathematics of the moon around the
yeah, just a second. Let me just bring up my app. All right. So here, right, when it comes to moon, what we got to realize is that moon, there is a phenomena called tidal locking. Okay, because of which the same phase of the moon we keep seeing the same phase of the moon. Okay, it's always the same phase. So basically, what happens is the moon revolves around the Earth at the same rate as it rotates on its own axis. So these two periods are exactly the same. It's locked. So that's why we say near side of the moon and far side of the moon. Okay, they are fixed sides, right? Some people refer to them as dark side and the light side, but that is a wrong terminology. All areas of the moon get lit and they also go into darkness. There is sun and there is darkness on any point on the moon. The right terminology is near and far. So since moon is showing the same face towards Earth, the center point of the moon disk, that we arbitrarily define it as 0 degrees in equator and the moon's equator. And with that, you realize that this is the equator, right? And then with that defined, you can define north, which points to the equator's north, right? And you define longitude running towards east, 0 to 90 degrees, and 0 to 90 degrees on the west. Okay. Just like Earth, you define longitude and latitude. So we have the prime meridian, okay, and which is running straight down, and you have latitude and longitude. So that's how it's defined. So that is a grid, correct? And this grid is well defined. But then let's go to the next. Given that that is how it is defined, let me escape. Okay. Right. Typically, this is rendered, as I said, with north up. But if you see a rising moon from Bangalore, let's say, it's a very low altitude, right? The pattern which you see is slightly rotated. So you got to realize that that's how it is, right? So if you see from Bangalore, like this is how it will see a rising moon. Okay, it's a rising full moon picture, right? But typically in pictures, we typically render it with the north. This is probably the east, right? Uh, the northeast will be tilted in classic diagrams, textbook diagrams on other way around, right? Not really pointing up, right? So now that that's how we know it's mapped. There are maps available with different projections. This is called an equirectangular projection. Okay. Let's see where people have landed, right? So where did Chandrayaan land? Chandrayaan landed near the South Pole, not exactly on the South Pole, in the southern regions. Its longitude and latitude is around 69 degrees south. That's why it's down south here, all right? And landed at 32 degrees east longitude, okay? So this vertical line is the meridian, prime meridian, 0 degrees, 32 degrees. 32 degrees also happens to be this, for the longitude of this crater, right? That's where we landed. There has been only one craft which has landed on the far side, which is the Changi 4, but this is how it is mapped, right? So now that's the mapping of the moon, right? And for moon, there are excellent maps available. These are from the Lunar Reconnaissance Orbiter, LRO, orbiting the moon. You can go there and then look at moon maps. So there are different projections available, excellent moon maps. Different filters up here. I can switch to globe if I wish. Okay. And very beautifully rendered. You can annotate, you can share. Excellent resource for exploring moon. All right.
What is the resource?
This is LRO Quick Map. So LRO is the Lunar Reconnaissance Orbiter, which has been orbiting moon in a polar orbit for a long time. It has mapped moon quite well. Now we have our own Chandrayaan 2, mapping moon to a even greater resolution. But this is publicly available, LRO. You can go there and you can use this. So this is how you might have heard the story, right? Chandrayaan 2 crash site, the crash debris was figured out by Shanmuga Subramanian, right? By comparing LR images before and after the crash. So he could zoom in and figure out that hey, there is a difference near the crash site, right? Potential crash site.
How often does this get done?
How often does this get updated? I'm not sure. We'll have to check
But
the website. I hope so. Yes, it does. It does. Yes, yes, it does. It does. Otherwise, we couldn't have found. It does. Uh, yes. Huh.
Because of protection issues, something like that.
I believe the surface is actually like that. Yeah, that is one reason. One reason. The second reason is the sunlight falls at a very low, shallow angle. So, in some of the projections, it might look that way, but I believe there are both the reasons hold. There is, in fact, it looks different. Even from looking direct, it looks different. Uh,
So if
I believe the strike pattern, right? Crater strike pattern probably could have been different.
yeah,
Are there? Okay, fine. Let's switch back to the presentation again. Okay. So this is our landing site is near, two craters called one is Manzinus, the other is, Simpelius, close to that. This is the landing site, right? Um, it's hard to, uh, if you see two images of the same crater, right? It's hard to compare. It's hard to know it's the same, mainly because the times at which they were taken, right? The shadows, the where the sunlight is coming from, what is the angle, which orientation you are looking at, what is the projection, they are quite different. So in my animation, right, for example, I'm just comparing, what is a landing site from an LRO image and what you might find in my animation, right? So you got to figure out, exactly how do the geometries align, and then that, hey, this is the same crater, and they are like, recursive, right? So crater at 10 kilometers wide, you keep going closer and closer, you might find a 1 kilometer crater in similar in shape. And again, if you go down, zoom in, then again you see similar pattern. It's hard to gauge the size of the craters, right? So that's about all the moon mapping side. So let's switch to the next quiz. All right. Next quiz is on live. Okay. So if you want, I hope everybody has a link. The link.
from the WhatsApp, no? Oh, okay. Great. Thank you. It's because they know that's it. Yeah, I see that. There's a gift at the box.
All right. All right, fairly straightforward. Let's move forward, right? Near side, near lunar south pole. Okay, that's of course the answer. Yes, far side, near side, right? So now that we have got basic understanding of how you can uh, refer to positions in space via a well-known, well-agreed coordinate system, we can try to plot it, right? So we can get points if somebody is giving those points, like a sequence of x, y, z, and then we can just plot it in a three-dimensional space, correct? You can project it to a 2D screen and then look at it. That's what has been done on the animation, right? So if I switch to these animations, uh, let's switch to geo. All right, look at it from the xy plane. So that's what you see, that this is the red is x-axis. It points towards vernal equinox, right? Roughly towards Aries, that you can see by looking at it. You can see, the pieces, uh, constellation up here, right? You can look at that, and if you go the other way around, you can see what is there. Okay, what is the other side? You can see Leo on top. You can see Leo, right? You can see Leo on top. Then it's Virgo, right? Virgo Leo border, right? So the red is a vernal equinox. There is x-axis. The green is the y-axis, 90 degrees latitude, longitude, and the blue is the z, or it points towards the ecliptic north, right? You can see that here you can see the Earth's axis as well. You can see the tilt. So this is, let's say, this is at launch time. How does it look, right? It's summer in the northern hemisphere, right? We launched in what, July, right? Few days after the summer solstice. Okay, 3 weeks after the summer solstice, right? So you can move around and get a 3D perspective, which was not possible with the schematic. Right? Get a scale. So this is to scale, and if you zoom out all the way, all the way, you can appreciate the scale, and that scale we saw in the demo, right? In the balls demo, correct? So this is a scale, right? And here you see that you don't see the second part of the pattern in the schematic, right? This is because moon is circling the Earth in a near circular orbit, and it rotates, right? So if you, from an Earth-based coordinate system, you will see a spiral like this, okay? Whereas from a yes, it is forming a helix. Now that you asked for it, let's see if you can spot that. Okay, let's pick up uh, the the insertion point. Let's zoom in. Okay, so right. So now if I play this right from here, go a bit faster. Okay, you can see the helix, right? You can see the helix. So that's the helix. You can align it whatever we want. You can clearly see the helix. All right. You can see the helix. So, um, so this gives you different perspectives to view the orbit, right? The same orbit, if I can view it from moon's perspective, right? I can put at LOI time and then I can render that. So you can see this is the moon orbits, right? And I can go zoom out and get the scale of this, right? So now if I zoom out all the way, right, you can see Earth here, up here, right? All right. So that's pretty far, obviously 3.84 lakh kilometers. Uh, and this is the other way around, right? So it's all relative, right? And you can see the scale difference, the distance between Earth and Moon versus this tiny lunar orbits around, which the craft is making, correct? So you get the right scale perspective by playing around with this, okay? And what we also see is that, which we will come to very shortly, is that this plane doesn't change, whether it's Earth orbits or Moon orbits. They are they are there, right? Um, they don't precess. So in the inertial frame, which you have defined as coordinate systems x, y, z, they don't precess. It's a solid plane. So I can look at it from x, y direction like this, right? Uh, they don't change, right? They don't change. What you see is that let me go to ZX maybe. All right. What you see, let's get to zoom in this way. We are looking at the south pole of the moon. Let's get it out of the orbit. Okay. Let's go to the launch position and play this pretty fast. Okay. I will keep the orbit maybe. Okay. This orbit. So what do you see? The orbit is same. It's a fixed plane and the moon rotates underneath it. Correct. So that's the kind of geometry we have. So the planes are stable because it's a polar orbit. There is no precession. There are, of course, changes due to moon's gravity not being very uniform. It's very tricky to get a stable lunar orbit, but more or less it's stable, right? You can see the moon rotating underneath the orbit. Okay. If you're careful, you can also see another motion. Do you know what I'm talking about? Another change which you can observe. So if I pause it at launch time and maybe pause it at landing time, what do you see? Hmm? The lit side, right? The lit side, there is a change in the sunlight where the sunlight is falling. That angle has changed. And why is that?
Celebration.
Hmm?
Earth and moon both are revolving around us.
Exactly. So the reason is that Earth and Moon are both revolving around the sun. And if you look at it from Moon's perspective, it's as if, sun is revolving around the whole origin, right? So the angle at which sunlight comes is changing. Okay, that's why you see that it's changing, correct? So here, we also see these 2 points which are marked. The green dot is the primary landing site, and the yellow dot is the alternate landing site, okay, as a backup site. You can see that they rotate, okay, they rotate. So all you have to do is, wait for it, and when the right time comes, you land. It's like entering a revolving door, right? When the door opens up, you enter it. Or like in some buildings, you would have seen a moving lift elevator, which keeps always moving. When the plane aligns, you just get in, right? So that's how the craft landed on the moon, on the craft, on wherever you want to land. It wait for it and then land it, right? So we'll come back to this, okay? Let's switch back to the presentation. So we can plot, right? And this data, right, is available from a NASA website called Horizons, JPL Horizons. JPL is a Jet Propulsion Laboratory, equivalent to our Liquid Propulsion Center in Indiranagar, right? Equivalent to that. They publish the data. Why? Because ISRO has shared the data with them, and for um, tracking via the Deep Space Network. Okay, we make use of their DSN antennae to track Chandrayaan because we don't have such antennae all over the globe. Okay, so we seek help from either the European Space Agency or JPL NASA, along with our own stations, ground stations, to track. Correct. So we obviously have to share the data, but this data has been made public, partly in a sense that I requested them around Mars orbiter mission time frame, uh, and I was able to have a contact with the the team handling the site. I requested them to make it public. So it started from MOM, moved on to Chandrayaan 2, and now to Chandrayaan 3. Okay. So with that data, you can plot. You can go to that site. Let's see if you can quickly log in there. This is the Horizon site, and you can pick. And if you search for Chandrayaan, okay, uh, you will find two boat lander orbiter, right? We were tracking it separately. 3, the lander, and 3P is the propulsion module, right, which has been now brought back to Earth orbit. So this data is available only if ISRO shares it. Okay. So now we have got the data only until around you can see here, right? If you see, look at the time, we will figure out until when it's available. So it's available only until 6th of September. Okay, not beyond that. You can see the min time and max time. Okay. So note that this is available, but only if ISRO has shared during that time period, not after that. Right. So if you have got it, of course you can plot it, right? You have the map. You got the map. So then, is that enough to quench your curiosity, or uh, should we look at more patterns, right? So you can look at it in various ways. So that's what we're going to do. Let's get back. Okay, let's get back to the slides. Okay. So these are, you start to see patterns. One can see this as a sequence of points X, Y, Z, or you can see it as structures. What are the structures around? These are orbits. And of course, there are Earth-bound orbits, lunar-bound orbits, and there is a transfer orbit. Okay, that's what we are seeing here, right? These are all elliptical in shape. Okay, they are essentially conic sections. Okay, the transfer orbit from Earth's perspective is a elliptical orbit, but from a moon's perspective, it's hyperbolic. Okay, it comes in a hyperbolic trajectory and then gets captured by burning down, right? Reducing the velocity, you make it an elliptical orbit, get captured in Earth's gravity, I mean moon's gravity, right? So we got to know more about orbits to really appreciate what's going on here, right? So we move to quiz 3. Before that, okay, what is quiz 3? It's visible. The answers here are jumbled. Okay, so they need not map to the same order in which you see the choices. Have any questions come up?
Till now, no, nothing online.
Okay. All right, let's move on. In fact, all the agencies tracked, and that's the right answer. All right. Um, ESA 2. Okay.
So how did the ESA track? Like we understood the JPL.
Yeah. They have their own ground tracking stations.
So what exactly was the contribution?
I need to check. I don't know. JPL was more, very deeply involved. ESA's contributions, I don't have the details.
But everybody has. I think this is a different part of it. So
Yes.
even that is not visible to JPL, it is visible.
Possible, but then JPL has, ground stations across, you can track anywhere, right?
So
So it was more, I believe, more of a strategic partnership because Aditya is tracked only by ESA and not JPL. JPL was involved only in the initial orbit design phase, but JPL is not tracking Aditya. So if you see, when I checked for the orbit data for Aditya, right, only preliminary orbit, orbit diagram is available, orbit data is available. JPL is not involved. So ESA is involved, and ESA is not sharing the data. You had a question?
JPL's monitoring stations,
Huh.
tracking stations,
Yes.
does that form all of the deep space network or other
They are complemented by our own deep space
so
network.
other parts of the world also?
Yes. Yes.
And why isn't all the data went from it? What would be the reason they would hold it down?
It's a policy question, right? It, it depends on what the political leadership or the leadership of the organization decides. It varies.
I mean, is the interest only?
We should ask as citizens. We can ask. We should ask. We should ask for sharing more data by public organizations which we fund. Right? It's our income tax money which is being used. So if it's not done through our representatives, we should ask for sharing the data more. Right?
Like kind of paywall or something, like if you to get that.
No. It is not shared. ISR doesn't share it.
Self-thinking government initiative, right? Shouldn't be asked.
We can. We should reach out to our representatives and push this forward. All right. So now we are still in the foundations phase, right? So let's cover orbits. So what are the structures, right? We are all familiar with orbits, right? Very familiar. Okay. We all know gravity, how it works. We see hyperbolas, okay, right? Parabolas. These are all conic sections. High school geometry. Okay. We can also try exactly what's going on here. If you see this side, helps you can add an orbit. Got an orbit here. This is called the closest point, right? It's called perigee when it comes to Earth. Apogee is the highest point, right? This distance, is a one axis, okay, and this distance, Earth is at the focus of the ellipse, the other axis, right? So now you can alter it, okay? You can alter the size. You can alter the how skinny the ellipse is, right? How circular or how skinny the ellipse is. You can change the eccentricity. That you can do on those two planes, right? You can also change. I have shown XYZ, right? You can also rotate the orbit. So you can rotate in this way. You can change the angle where the perigee and the apogee are. The line of apsides. The line of apsides can be rotated, right? These are all in the XY plane. And you can also see that if you go in 3D, right, you can change the inclination. So now you can change this inclination. So now you get a 3D orbit. So any orbit in space, you have some fundamental parameters like its semi-major axis, right? It's half the length of the major axis. Um, its eccentricity, what is the angle of the orbital plane with respect to the reference plane, xy plane, what is the angle of the perigee in that plane, is it aligned with the apsides or is it away from the apsides, right? So these are all completely define or characterize the orbit. Now when you are planning a mission to moon or planning any spacecraft mission, the designers of the orbit have to think of all these things. What do I do? What kind of parameters do I keep to reach the moon, right? To orbit the moon. So often, you will see that what should be the semi-major axis? What should be the size of this orbit? Okay, where should I point it to? These are problems which have to be solved, right? So our idea is just to know that, hey, this is how orbits are characterized, and uh, so that we know, we can appreciate when we look at an orbit, how has it been designed, right? So now, given that we have seen a bit of it, right? Let's switch back to the animation and see right here, right? So this is the Earth-centric view again, and you can see that the perigee, right, the closest point, is actually pretty close to Earth. It's just 170 kilometers altitude, 170 kilometers. Okay. Whereas this apogee, right, there are multiple apogees here in orbit 1, orbit 2, orbit 3, orbit 4, and multiple apogees here. They are all extending, and the highest apogee before we got transferred, right, uh, that's easily 1/3, I guess, the moon's distance. The very first apogee which you see here, right, up here, this point, okay, second, for this, probably can do this. Does it work? Still doesn't work. Never mind. Oh, there you are. This is the first apogee, right? This is essentially a GTO or a geo transfer orbit. Okay. Uh, so essentially we have a GSLV, which is placing the spacecraft in a GTO, right? So its apogee will be close to what GTOs achieve, right? Which is the distance at which geostationary orbits revolve around the Earth, which is about 36,500 kilometers, right? That's what it is, correct? And then goes all the way up. Another important thing which you can see is that if I put it on a ZX plane, maybe XY, all right, XY plane, right? I'm in the YZ plane. Okay, so that means I am looking from the vernal equinox point. I am at the 0 degree point. I'm looking at the 180-degree point, right? That's where you see Leo and Virgo. Okay, uh, I will add here the equatorial plane. Okay, see that, and the ecliptic. This is ecliptic. So let me add. Now both are added. You can see the angle up here. This is 23 degrees, 23.5 degrees. And when I click the timeline, I will click uh, as a LOI point, right? Lunar orbit insertion point. So I can see that this is close to the equatorial plane. So what I'm doing, right? What is being done is you are targeting the moon's orbit when it intersects the equatorial plane. Essentially, we have a GTO, right, orbit, and to reach the moon, you have to go all the way to the moon's orbit in distance. But where do you intercept it? You can intercept it only when the equatorial plane intersects the lunar orbit, because we are remaining in the equatorial, in the orbit which we launched and which is close to the equatorial plane. And then when you hit it, you have to hit it at the nodal point. So that is how this orbit is designed. So you can see that, this is at that level, right? The green is pretty close to equator. And the yellow thing which you're seeing is the ecliptic plane, right? Which is at 23.5 degrees. So we will see as we progress further, how this is done. Probably won't go into specific details up here, the references, you can use it as a reference, but get an idea that, that's how orbits are defined, right? So if you take the data available from ISRO website, they published notifications messages after every orbital maneuver, and then they say that this is the orbit size. Okay, that's what is plotted here. But you can know that what this means. This is the the apogee height, and this is the perigee height, and you can see that successively they have increased the height all the way up to 369,000. 384,000 is the lunar orbit size, right? And then you cut down, cut down, cut down, and reach. Okay. So yes, 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 correct. Yeah. So point is, you really don't have to change the perigee. Answer is that we will come to that. We will come to that in a bit, right? So now we have known the structure, right? As a geometric structure you have seen, but now we have to see how it moves in terms of gravity, right? So you can treat an orbit like a common experiment in physics is a hypothetical experiment, right? It's like uh, you can imagine a cannonball being fired. Okay, if you have very little velocity, it will just drop down up here. Okay, start increasing the velocity, it will keep falling farther and farther until at a specific velocity it will go around the Earth. Okay, and beyond that it will still go around the Earth, but in various eccentric orbits, and eventually it will escape the Earth, right? If you go beyond the escape velocity, right? So this again, is I'm going to GeoGebra. There's a nice animation somebody has put together, right? So if I go here, I'm pretty close, 170 kilometers. Okay, all right. My velocity is about 10.3. 10.3 is the velocity at which our craft put the orbit in the initial orbit, initial parking orbit. So now, sorry, 10.3 kilometers per second. Yes, correct. So now if you zoom out and see what is the periapsis altitude, right? So if I go up here, right, its altitude is about 38,000, which is roughly the GTO orbit, right? Geostationary orbit. So now you can play around with this and see what happens, right? So you can, in this, see, so now I have got a very, almost a circular orbit. Let me get it right. Right. Yeah. This is like this is 7.8 kilometers. Perigee velocity 7.8 kilometers. I'm at an altitude of 170. I almost get a very low Earth orbit. Okay. Now you can see that if I increase the velocity, right? If I increase the perigee velocity, what happens? The apogee increases. Keep increasing, right? So I can go all the way up, and I can change the angle to change the apsidal angle, right? The line of apsides change a little bit if I alter this. Okay, so I can go all the way up, but then beyond that, this graph cannot render hyperbolic orbits. It can render only ellipse. So you don't see that, but we are concerned only with elliptical orbits, right? So you can increase and change it. So what's happening is you are basically adding energy to the orbit. The energy is only depending on the size of the orbit or the semi major axis of the orbit given a system, given a two-body system like Earth and a spacecraft. Energy is only depending on the size of this orbit. What's the the A pointed out here, right? 22,755 kilometers. That is a semi-major axis, half the length of this major axis, right? That's it. So you're adding energy by putting additional velocity here, and it changes. And then you can do other things like maneuvers. You can go, once you complete half the orbit, you are at the other end, right? And then you can apply additional velocities if you want to go in circle, or you can keep adding velocity the next time. First time you added a little bit, so you start like this, you add a little bit, first time you add another little bit, next time add a third another time, and you extend the orbit.
So this is the typical slingshot maneuver.
No, this is not the slingshot maneuver. In slingshot maneuver is different. This is what is known as an Oberth maneuver or an Oberth effect. So what really, I will come to that, So what really happens is, let's go to the slides again. Yeah, here it is. Since you asked the question, right, whether it's a slingshot or not, this is what is known as an Oberth maneuver, wherein the question is, to add energy to the orbit, what is the best place to do it? The best place to do it is when it is at the maximum velocity, because energy is proportional to square of the velocity, or v squared, and v is highest in and the perigee level, right? So what you are really doing is, you are transferring the momentum in a rocket fires when you add a specific delta v. But then what you essentially do is that, then the question is, you have to split that energy between the expelled fuel and the rocket. So when you do expel the fuel at this perigee point, you are dumping the fuel and it probably has very little velocity because it is going at the opposite direction. So the proportion in which you divide the energy is such that the rocket gets most of it, and the expelled, dumped fuel, burnt fuel, gets least. In turn, the energy of the orbit increases quite high. So effectively, you are making use of that principle, and that's what you have done in raising or reducing Chandrayaan orbits, whether around Earth or around Moon. So you always do the maneuvering at perigee, the closest point, periapsis, right? And this is also, like an example out here, from a physics example. Where do you fire the rocket so that you can reach the top of the hill on the right hand side? Do you fire it at A or do you fire it at B? Right? The answer is you fire it at B. Okay, where the velocity is high. Okay. Did I answer that question? And Kirti, you had a question.
Basically, kind of imagine what opposite steps.
Yes. So here, right, I think to answer the question in a few things. Okay. So let's look at this animation up here. Okay. So what is happening here? So if I'm placing a point here, okay, anywhere, okay, and I'm picking a velocity. Okay. So I'm specifying r, the distance from the focus, and I am defining a velocity, which is a magnitude and angle, correct? Together, right, they determine the complete orbit. Because I'm just dropping something, and then that determines this complete orbit. So if I change anything, right, the whole orbit changes. But the point is that whatever I do, right, I have to be in that point. The orbit, the spacecraft can go and come back, but it comes back to the same exact point. So whatever I do, I am in an orbit in which this point is part. So it's not like magically, the orbit changes and I end up with a larger orbit where this point is not part of. So that's the main point to note. Whatever I do, right, I am part of that, except when it's a hyperbolic orbit where I escape. As long it revolves and comes back, right, I will come back to exactly the same point. Exactly the same point. So it could be a circle, it could be an ellipse, but I will come back to the same point. So then the question is, so it doesn't change. So the perigee, if you are doing it as a perigee, right? What is perigee? You fire it at 90 degrees, right? And then that becomes a perigee, right? Or if the velocity is too low and I'm still firing at 90 degrees, it becomes apogee, right? So now to change perigee, you have to do something on the opposite side. See, if you have to raise the perigee, I will have to do velocity addition on the opposite side. In that case, my apogee will change, right? So if I assume that, let's put it in a different way. Let me take this point here, all right? And I will put up a velocity such that that point is, okay, where is it? Okay, there you are. So now this is I put only enough velocity so that it is apogee, right? If I increase it, that it becomes perigee. Okay, so let's assume this I am at apogee, right? So now to answer Kirti's question, I will just increase this, perigee increases, increase it, perigee increases. At some time it becomes a circular. Then if I increase it further, my own point where I am in, right, that becomes a perigee, from apogee to perigee. So the change happened on the opposite side, because I have to return to the same point. As long as I'm in an elliptical orbit, I will come back to the same point. So that's the principle there, right?
So just as an extension, if you're putting the spacecraft in a circular orbit around the moon,
Yes.
so this is what it has.
Yes, this is what we'll have to do. Yes. So what we're doing is that, again, showing the animation, right? Suppose I am in an orbit like this. Okay. I am in an orbit like this. Let me bring down closer to the point. So now I need to circularize it. Okay. So what I have to do is I have to reduce the velocity. So I have to fire the engine here in the downward direction, opposite to the velocity. So basically, this velocity, let's say I'm at this velocity. If I reduce it, right, orbit shrinks. If I reduce it further, orbit further shrinks. Reduce it further, it shrinks further, right? So that's what I do at perigee to shrink it. So I'm bringing down the apogee. In the case of lunar orbit, they are called aposelene and periselene. At periselene, I fire the motor so that I bring down the velocity. Then the aposelene comes down, comes down, comes down. This is exactly the maneuver which you use to reduce the orbit. Okay, that's it. So that's a basic principle. Okay, so all of this, I'm not getting into math here. You can derive equations for simple two-body problems with basic +2 physics. Okay, there are equations to look at the energy and all that. Again, I'm not looking into that. You can yourself compute the velocities at which the orbit is placed. So let's try it out. You can see that the translunar injection, right, at that time it was 10.8 kilometers. At 170 kilometer, right? You can try to do that. Keep it close to 170. I think that's 6,300. That's Earth's radius, right? And I can keep it. We are at very abscissa altitude. Still perigee close to 170. See, 3152. You can experiment that and get all the way to increase it to 384,000 kilometers, right? About at that 10.7 or 6 kilometer. Okay. Play around with it and you will get there. 10.6, 10.7. I've reached 95,000. Increase it further. All the way. And you will get the LT object. You have to play around with it and get it, right? So that's what we are doing. Okay. So we'll skip the next quiz. Probably we'll go to maneuvers about the effect we talked about. What we exactly which you are doing in Chandrayaan's case is raising the orbit, right? That's exactly we are doing. So we talked about this. Basically, we are applying what is known as a delta V in additional velocity at the closest point, so that the opposite point raises. Okay. So essentially, you're adding energy, right? Adding energy to the orbit. So at this point, it's a kinetic energy that sort of becomes, converted into potential energy at highest point, right? That's what exactly happens when you throw a ball up, correct? Its kinetic energy drops, then the potential energy increases, total remains the same. Essentially, you're adding energy to the orbit, right? And the most efficient way to add energy to the orbit is at the closest point. And that's what about the effect is. That's what you do, right? So if you want to increase the orbit apoapsis, you increase it. So how do you make use of it? The way we make use of it is that we increase this apoapsis further and further until it hits lunar orbit. So we are reached to that point, correct? We can reach up to lunar orbit by increasing this velocity. Because we don't have powerful enough rockets which will give this delta V in one shot. We do it successively, step by step. It's the cheapest way to do it, right? So if you take Apollo, right, it had what is known as a direct transfer orbit. So it had very powerful rocket, the Saturn V, and it did all the way. It not only put it in a parking orbit, but even the lunar injection was done by the same rocket. So enough delta V was added to reach up to the moon. But our GSLV is not powerful enough. So all it can do is it can reach up to 36,000 kilometers, which is the GT orbit. Beyond that, we have to successively use the fuel in the craft to add this delta V in multiple steps, in 4-5 steps, so that this point, right, this apoapsis point, reaches the moon's orbit. Correct? Then when it reaches the moon's orbit, we have to time it and angle it in such a way that moon is there. Otherwise, you will reach, but moon is not there. Right? So you have to time it so that when you start this journey, right? When you start this journey, you end up intercepting it, right? So if you go again up here, right? Let me get rid of this planes. Let's start with the TLI. TLI is here, right? Uh, Let me zoom in here. Okay. And if I play, you can see the craft going. This is the transfer orbit. Where is the moon? Moon is not to be seen. It is coming up somewhere. Where is it? Maybe down somewhere. There is, there is, there is, there is. All right, make it a little bit faster. All right. You might assume that it might miss, but it won't because this is slowing down. As it reaches the apoapsis, it's slowing down, slowing down. It's probably 0.2 kilometers. Then it slows down to such an extent that moon catches up from behind and then grabs it, and then it gets grabbed by the SOI and runs it. Right? That's what happens. So that's the technique you use. So point is, you are firing it, like at a time when moon is somewhere, and then when they both meet, it is like the impalement arts, right? When in circus they throw knives in a rotating platform, right? At the target girl. So you time it so that it hits the gap and not the person. It is like that. It's exactly like that.
So, basically,
Yes.
so it's not only, till now, my understanding was when you launch a craft to reach a certain target,
Yes.
primarily what you considered was local atmospheric conditions, and beside the launch conditions is
Yeah.
something critical.
Yeah. Yeah.
Other than that, there are so many factors that go into play.
Yes. Yes.
Ensuring it-
Yeah. Yeah. Yes. 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 Correct. Yes, they do. Yes. Yeah. All right. We will look at the factors in a bit, right? So now they have seen this maneuver. We can also reduce the orbit. Okay. We can do it reverse by again burning at the periapsis. Okay. Now there is something known as Hoffman transfer, right? So this is where you use exactly the same technique to get from one circular orbit to another circular orbit. So this is used in the Mars orbiter mission. So the inner orbit, you can say, assume it's a Earth's orbit. The outer orbit is the Mars orbit, right? You add enough delta V to put it on a transfer orbit. But then if you leave it here without applying delta V dash, it will keep circling in an elliptical orbit like this, right? It doesn't have enough energy. Its energy is equivalent to half the orbit size, right? It's roughly this, correct? It's that size. So you have to add more energy. That energy you can add it at the apoaxis side and then circularize it. Okay. We don't you know exactly use that in the uh, we use something similar for Chandrayaan, right? We get to the moon's orbit, and then we uh, align it with the moon's orbital speed, and then it gets captured. All right. So this is a generalized case, two ellipses. Okay. But what happens when these are in different planes? So like this, right? So if you do it here and you want to reach, assume that the black arc is the moon's orbit, and this is the Chandrayaan 3 craft orbit. You keep raising, but it's of no use because the planes are not aligned. So you got to figure out how do we align the plane, and then then get it to the same. Uh, you target it so that your the farthest point intersects the other orbit. Okay, so that's what you can also see here. If I put this animation in this form in the YZ axis, right? Let me draw the equatorial plane. Okay. And this is the moon's orbit anyways in this plane. So if I look at it TLI, lunar injection, and then play it. Moon is here on the left side. You can see that. Okay, faster. So it's not the distance which is the same when they align, right? It is the angle also which gets aligned. So you can see that, if I again play it again, moon is here. Look at this angle. Look at this angle. This is equator, right? So it's at a very low declination. It's in the south, right? Southern hemisphere. And it crosses the equator here and it goes to northern hemisphere. This orbit is at an angle, right? You intersect. So you intersect exactly like if I were to show here, right? Uh, take this, put it here and intersect, right? So you are putting it in a way, such a way that uh, you have to target the orbit upper axis so that let's say this yellow, right? Let's say it's at the intersection point. It's at the intersection point. Yeah, that's okay. I think it's it's all right. We'll stop that. Okay. Now, continuing, correct? The delta V map, I'm not going to spend time. Rocket equation. What matters is, this delta V has an exponential relationship with the mass ratio. We are not getting into rocket propulsion and all here, but it becomes very, very difficult to add delta V. The rocket size becomes enormous. It's very huge. We don't have that capability yet. That's why we do this trick of doing it iteratively, okay, each time. Otherwise, you can burn, but that burn will be very long. And then, you will go beyond the periapsis, right? You will go beyond, you have to burn it for a very long time, and then it won't be efficient, right? So that's what we're doing. So we do two kisses now, all together, both. Right?
I have a question.
Yeah, no. Yeah, that's perihelion, right? Um, Next quiz.
Flow rate needs to increase the velocity.
Yeah. Yes. Correct. Yes. Prograde is increasing the velocities in the same direction as the current velocity vector. Yes.
It should be. So the orbiter's orbit is in which plane and respect to us.
It's at an inclination of around 20 degrees. Sorry? Uh, In the sense,
When we launch it,
Mm.
so could we put it in the elliptical plane itself, the orbit of the orbiter?
yeah, there are constraints to that. So basically, we are at an altitude, right? We are at a latitude. The launch Sriharikota is at 13 degrees latitude, around, right? So that means, and we have only specific angles at which we can launch because we have to be safe in the downstream path. If the rocket has a failure and the first stage or second stage falls down, it shouldn't affect anybody living in the path. So we have constraints on what inclination we can launch. And those inclinations, define essentially for Sriharikota, either you can launch at 21 degrees inclination or around 48. You can go higher, but it is constrained. There are only specific values possible. So you get a specific inclination. So you can launch at around equator, right? Because this is essentially a GTO. So in a GTO, you will stay close to the equatorial plane. The only thing you have to match is where am I targeting the perigee. So if I am targeting the perigee, I am at the equatorial plane, okay? And if moon is intersecting there, right, at that point, then I will angle it so that my apogee, right, is hitting that node where it dropped. That's how you plan. Okay. So in this case, right, this is the let's look at. So it's a prograde. You have to actually do a prograde burn at apogee. Okay, that's how you circularize it. Okay. All right. So now we have covered all the basics. So any questions at this point, right? We will cover the design in a bit, right?
This one.
Yes.
Questions pertaining to our orbital.
Yes.
So let's say that in a hypothetical situation,
Huh.
our launch is delayed by a day or two.
Yes.
So would we still be able to?
Yeah, we will still be able to. I am coming to that. I am coming to that. Any questions? Yeah, I'm coming to that. Yes. The rest is all, about that. How do we get there, right? So mission design is, primarily lunar orbit, right? So how do we look at the lunar orbit? So what do we want to do? Okay. We want to land at the primary landing site, which has been identified due to the science we have to do, right? So there are science goals, and those science goals have identified that, hey, this is the place on the moon I want to explore. Okay. So by that, it's somewhere in the southern polar region, and we should be able to land relatively safely. It shouldn't be in the middle of a lot of craters. You identify a site, and there you have to land. But when you land, you got to land um, at a specific time. So suppose you are going to Bombay from Bangalore for a business trip. You have a whole day's work. Okay. When would you go? You will typically take a morning flight and land, let's say, at 8 a.m. in Bombay, right? So you're landing at the beginning of the day so that you have the whole day to do your work, and then you can come back in a late night flight. So similarly, you are landing at the primary landing site, and you have to land at the beginning of the day. And what is a lunar day? It is a lunar day is around 15 Earth days. Okay. One synodic month, right, is 29.5 days. Half of that, right, 14.75, roughly 15 days, is a lunar day. So you have to be there at the beginning of the day at the site. So that's when you've got to land. Okay. So that sort of determines that, when you can land. So if you see here, so that's what you're going to see, right? And at the time of landing, there must be sunlight. It's not that it is exactly sunrise. Sun cannot be at 0 degree altitude, right? It is just rising, it's on the horizon. When you land, you don't have enough energy for your lander to power up and bring up the systems. So it has to be at a specific, it should have risen at least somewhat. And what is that range? We are looking at 6 to 9 degrees altitude. So you're looking at 6 to 9 degrees altitude, which is roughly 2 days after the sunrise on moon. In the 15-day window, it is roughly 2 days after that. Okay, roughly. Okay. So you can only land at that time, and then you will get to spend about 13 days beyond that. Correct. So these are the constraints you would look at when you're about to land. So that means if you have to land, so you have only one landing opportunity in a month. Why? Because a month, our Earth month, right, which is 30 days, has 15 days where there is sunlight on the landing site on the moon and 15 days of night. And you have to land at the beginning of the lunar day. So that means, you have only one opportunity per month to land. That means you have 12 opportunities in a year to land. 12 opportunities, that's it. So now you have to time it. So that means, you got 12 opportunities, right? Now, how do you arrive at that, when to land? So you can see this again, getting into some detail. I will skip that. So I'm going to go to this animation up here. Okay. Let's go there. So this talks about moon's orbit around Earth. Okay. What do you see? This is a animation from NASA. The moon and Earth are not to scale. Orbit is not to scale, but angles are correct. What you are bothered here is only angles, so it is okay, right? So you can see that there is a sunlight, right? So there is a sunlight lighting up half of the Earth. The same sunlight, same angle. You can see when you see here, right? This sunlight comes in this way. Here also it comes in this way. Okay. Uh, let's run it. Let's run it a bit. And you can also see that there is a blue cross here, right? What does the blue cross mean? It means that it is shown to tell you how the moon is pointing towards the Earth. The same face points towards the Earth, right? That's why the blue cross also turns. It turns. It turns, right? It turns. Okay. So let's go to the beginning. Okay. Maybe let's see. Let's see if we can identify a, a place where we can spot it and uh, so let's take this point, right? So where is the sunrise on the moon? Annotate it. Okay. Is it? And we are okay. So I'm pointing one point. Okay. Let's say there is one point here, and there is another point here. Okay. Let's call it B, and this one let's call it A. Very bad annotation, but you get the point, right? So there are 2 points. One is this. One is this. Let's call it A and this B. Where is the sunrise happening? A or B? Hmm? A, right? Because it comes to the sun, right? Now you can see this point. So let's this is the point I'm referring to, right? This point is now well in the sunlight. If you go back here, it is not. Okay, it's just about has come out. That's it. So uh, it is now in sunlight all the way, all the way. It's going out, going out. Now it is sunset. So now you can see here, right? It is sunset. It's now at sunset, right? So let's go back and see where it starts to uh, where does it come into the sunrise? Okay, probably here, around here, maybe around here, right? The beginning. So this is where it's let's see if I can annotate this. Yeah, roughly at this point. Okay, let me draw that more better. Maybe around this point. Okay. Now, when I go further, right? Um, let's see. Let's get rid of it. You just remember that that's where it is. This is, this animation goes full 12 months. So if I keep going, you can see that. Did you see that change in the Earth's sunlight, this angle? Initially at the beginning, it was this way. Yeah. Where do I? Oh, here it is. It is this line. All right. And once I go beyond, okay, then can do that. Let it run a circle. It's gone a one full circle, and you can see that it is angle has changed, right? Uh, if I were to do, yeah, there you are. It's at maybe here. I'm bad at drawing. You get the idea, right? It's 30 degrees changed. All right. So now it is not that it is every month there is only one opportunity. The angle at which you have to land also changes 30 degrees every month. Okay. So now these two determine, right? These two together determine, where we are, you know, um, how do we choose the landing site? Okay. So we have seen that this is what it is. So what it finally, what comes to that is that uh, the orbit, as you have seen, right? It's a specific plane that has to align with the landing site, and that happens in a month. It happens on a specific day. So once you decide the day, once you decide the month, you get a specific date. Like for example, here, right? August 23rd. This is aligned. This is the landing site. The green site, the alternate landing site is yellow. August 23rd, you are aligned. Exactly, it comes. So you can see. Let's go to the animation and see that. Um, all right. Let's look at. Let's look at. Start from LOI, lunar orbit insertion. TLI. Okay, from TLI side. Let's play that. Okay, let's see. I think that has exceeded. Okay, yeah, let's play. So this site is now going into night. Okay, it's going into night. It's going into night. And it is in the middle of the night. So you can see the date here, August 16, 17, it's increasing the date. Okay. Now it's just about sunrise. What is the date? August 21st. Okay. If you play further, right, what will happen? 2 more days and it aligns with orbit. And that's when we land, August 23rd, right? So there is in every month, so this angle, right? This angle is determined, right? It's an angle at which sun is at about 6 to 9 degrees altitude. That determines this angle. Okay, this angle is known as right ascension of the ascending node. It's a orbital plane angle on the moon. So that is determined by the month or the sunlight. What is the sunlight angle? So when you determine that, there is only one opportunity per month to land. And that's how you arrive at what should be the angle of this orbital plane aligned with when the site aligns with the when we can land, when sun is at 6 to 9 degrees. You can also look at you can look at this at in stellarium.
All right. Thank you, sir.
Ah,
We have 5 minutes. Continue.
yeah, we will wrap up in about 15 minutes, right? We'll extend a little bit. Right, in stellarium also you can actually go to stellarium and you can pick moon. Pick moon. Okay. You can look at Chandrayaan. Chandrayaan 3 landing site. All right. We are in moon, and we can look at the time 2023, 8. Landing time is 23rd, right? It was about evening 6 o'clock UTC will be about 12:34, right? At that time, you can go check where we are, right? So uh, this is, you can see the Earth. If you are at that time, you could have seen the Earth in this way, and also you can see sun is up here. All right, and you can see sun's altitude here. It can see that altitude around 8 degrees, 8.5 degrees. Okay. So in the 6 to 9 degree window, it landed at 8.5 degrees. Okay. We have lost already 2 days, but we could have done anyway before that, right? So that's how you chose the landing time, right? So now this is getting into details, what is the angle, geometry, and all that. But essentially, that is the point. So the point is the landing site should come at an angle where sun is at 9 degrees altitude, 6 to 9 degrees altitude, and you choose the plane, and you also hit a specific date where you have to land. Okay, in a month there is always one date in which you have to land. Okay, if you miss it, what happens? You look at this animation again. This is an alternate landing site. So you play that again, and after 3 days, 23rd, 24, 25, 26, 27, the alternate site comes into angle again. So you have a backup plan. If you miss the primary landing site, 3 days you wait, keep revolving around the moon, and the alternate site comes in angle, and you get in at that time. So that is how the landing date per month is planned. Does this tell you, how to do further? There was a question, right, about when do we initiate the transfer, right? What is the launch window and all? We not come to that, right? That's the next part, right? So now we know we are working backwards. So we know per month there is one date at a specific angle you land. What about the transfer orbit? So there are different ways we can send stuff to the moon, right? The top left is the Apollo orbit. Then there is something known as the weak stability orbit. We are not looking into that. It goes to Lagrange point and comes. So it takes a lot of time, 100 days. But ours is, like you put it in a GTO and increase orbit. Okay. So that's what you have chosen. So what we do is that, here we have to intercept moon's orbit when it crosses the equator. So you look, there are only 2 times when it crosses the equator, right? In a month of 27 days, right? It revolves around Earth. Once it crosses, going north, south, another south, north, right? There are 2 points. There are 2 dates where it crosses the equator. So you pick a crossing point which is a few days prior to your landing date, so that you get a buffer, you get time to deorbit, right? When you intercept, you are at a very high orbit, high energy orbit. You need time, a few days, to bring down the lunar orbits. So now you look for, hey, I am landing on August 23rd. When is it that the moon is at near equator prior to that? Okay. In our case, it so happens that happened around August. Lunar injection was around August 1st, I think, August 1st or 3rd, one of the days, right? Where the declination was close to zero, close to zero. So now you can look at that part. Okay. Yeah, moon at LOI. This is again a stellarium screenshot where this is the equator. At LOI time, it is bang on equator. Okay. So you have to intercept at LOI point. So you got the LOI point, which is, I think, August 1st. Okay. August 4th, I think. Okay. So if it is August 4, you work backwards. So you got a transfer orbit, which is hitting moon on August 3rd. And this transfer orbit takes a specific time. There is no escape. It takes 3.5 days. Okay. 3.5 days. You can work it out easily, right? So, so that means I should have done the final delta V to push it to the transfer orbit about 3.5 days prior to August 4th, where the TLI injected, right? So, so you got the landing date, candidate date. Then you figure out the intercept with equator. That is your lunar orbit insertion, LOI. From LOI, you subtract 3.5 days the time of half orbit to the transfer, right? You get the TLI time. You got the TLI time means, you should have launched a few days prior to TLI because you have to do all these orbital maneuvers, right? So that's what comes in the final launch orbit, right? So we have launch is from Sriharikota and we can only launch at specific angles. Okay. That determines the launch orbit. So this is what we have been saying. LOI timing is determined by moons crossing equatorial plane, 2 opportunities per month. Line of apsides, the apogee, perigee, is based on where is that intercept, right? Is it here? Is it here? Right? And you determine the TLI time. And then you can launch, maybe 2 weeks prior to that. You just need time to do the orbital maneuvers. That's it. So in that whole time window, you get a week-long time window for any landing opportunity, typically. So you can launch every day. There was a question, right? You can launch every day in a week. You just need to time on that day, a specific time you have to launch, so that you get the angle correct. Okay, you get the angle correct so that that points to the intercept point, because it's very it takes energy to uh, change an orbital inclination. So you don't want to do that. So you typically keep the inclination same, and if you are doing that, then you have to hit the time right. Okay, right? So that's the logic. So this is the whole logic which is given here, right? Which is based on a paper on Chandrayaan 2, but more or less the logic is the same, right? Essentially, you are looking at the science goal and you arrive at the primary landing site. Then you arrive at the alternate landing site 3 to 4 days from there, right? Once you get the PLS, you get 1 day per month. Okay, so you get 1 day per month, and that will tell you the angle at which you have to land on the moon. And then you get the LOI epoch, the lunar orbit insertion epoch, based on the intercept point, right? From that you get the TLA epoch, which is 4 to 5 days gap, and then you need time for all the successive maneuvers to do. So you will end up with something like this. So this explains, this is a whole timeline, right? This explains, how in the moon phase, you have a landing date which is fixed. Then you prior to LOA date is based on the intercept, right? There were about 18 days. And then, the whole LTT phase is fixed 4.8 days. And you have the Earth phase, which is about 17 days. So you are giving yourself enough time to correct the orbits. If some burn is missed, you can you get another opportunity, right? So you have enough time in the roughly 2 weeks plus time period to do all the maneuvers and then get there. So that is how the whole trajectory, the mission is architected, right? So questions.
So I mean, like, plastic, plastic,
Ah, yes, yes.
how much, how much time do I need to actually check how much?
Yeah, so this is known as orbit determination. Okay, so essentially all the ground stations, what they do is they collect the telemetry. From the telemetry you derive the actual orbit. So it is possible that after every burn there is a small error introduced, which you will correct it in the next time. So we have a low margin, but you can correct it. But what happens is, if you correct it, you spend energy. So you have to burn the rocket, you have to tilt the angle inclination, or you have to change the apogee a little bit. You all spend up burning energy. But when you design the whole orbit architecture, you put enough buffers so that you have enough fuel for all this. So Chandrayaan 3 did a very good job. That's why it had a lot of fuel left so that we can bring it back. So that way it did a tremendous job, tremendously good job. So you can go wrong in the apogee height, right? So you may not hit, let's say, 36,000 kilometers. So you may probably be 34,000. So you may need another burn. Or it is possible that the inclination is not exact. the intercept inclination is slightly off. You have to correct it. You keep buffers for all that.
And from the different dynamic side, how far
I think we were um, pretty close. It was a 4 by 4 kilometer area, I think. I need to check exactly how much is that, but I think it was close. And if you have seen the um, live session, right, I think it also retargeted it because the initial site was not good enough for landing and it moved a little bit. Yeah.
so you told that this maneuver is for Oba.
Ah,
How does it compare with the slingshot?
yes. So in Oberth maneuver, right, you have to see that um, you have a spacecraft with propulsion. Okay, there is a momentum exchange between the fuel and the craft. All right, and you are adding a velocity because of that. Right, that's about it. Right, and you are doing it at a place where it is closest, and it is moving around the object with most velocity. That is Oberth effect. Right. In slingshot, what happens is you are looking at the velocity from a next level object. For example, when you talk about slingshot, right, you're typically talking about an interplanetary orbit where there is sun. Okay, there is a sun, there is a planet, and there is a craft. Here in Oberth effect, there are only two bodies. There is an object and there is a craft. That's it. But in slingshot, gravitational slingshot or gravitational flybys, you are essentially exchanging momentum between the planet and the craft, so that your rotational velocity around sun is increasing. Okay, that's what you're doing. So there is a momentum exchange between the planet and the craft relative to the sun. That's what you're doing. But in Oberth effect, there is no such sun equivalent body. All the momentum exchange happens between the fuel and the craft. That's it. So that's the difference.
Let it be star. Okay, it could be slingshot. I will be slingshotting around the star.
Yeah, you can if you are able to design an orbit like that. And what you want is essentially related to the sun. You are able to uh, gain that additional velocity. If that star is able to give some momentum to the craft in our desired direction, yes, you have a slingshot.
But slingshot is used to change directions.
Yeah, effectively you are changing the velocity, right? So you're it's gaining, it's the velocity vector is changed. It could result, basically it's adding a delta V, right? The planet is adding a delta V that will result in an angle change. So that's what you see. Without fuel, yes. Because basically there's a momentum exchange in the whole system. In the overall system, we are not, defeating any laws of conservation of energy or anything. It is just that energy is transferred from the planet to the craft to our advantage. That's it. Yes. Yeah. The planet gives some momentum to the craft. Yeah, if you want to increase the velocity in the same direction as where the planet is going, you put it in that way and you can do that. Yes. Oh, is it? Okay. Oh. All right. Yes.
The spacecraft is already taken. Right.
It, not really. So basically, when you are circularizing, correct? Are you talking about the Hohmann transfer or are you talking about something else? Hmm.
Was formed around orbiter. When we are putting the Chandrayaan 2 in the orbit,
Uh-huh. Yeah, we are reducing the perigee velocity. So yeah, basically you have to reduce the velocity, right? You have to reduce the velocity at perigee so that you have to fire the motor in the opposite direction. That's why you reduce the velocity. Hmm? Yeah. So basically, there are. It's not there are thrusters which you can angle at any angle you need. So you can control you can do a yaw maneuver. You can turn the craft 180 degrees so that it points to the direction which it's going, and then you can fire the engine there. Orientation. You can change the orientation of the craft. Yeah, but it will consume a bit of energy. Not as much, but it will consume. Yeah.
It goes in the same direction, but it has only turned.
It has only turned, yes, correct. And you reduce the velocity. That's it.
Good that you started.
Yes.
Well,
Because if you exactly landed on sunrise, sun will be at 0 degree altitude. There won't be any sunlight, usable sunlight. So there are two reasons. One is that you have to image the site when it comes in sunlight, correct? Because you have to know, am I landing at the right place? So there was an imager on the orbiter which matched with pre-existing images, right? It did a matching algorithm and it figured out that, hey, I'm on the right track. So that needed some sunlight. And that sunlight you had to have, sun had to be at least 6 degrees in altitude to get that picture. Otherwise, you wouldn't know where you're landing. You are doing a blind landing otherwise, right? So you needed some light to pattern match. Then you also need light for energy. So that's why the 2 days gap, roughly 2 days gap.
So the pattern matching happened all on its own. I mean,
All on its own, yes.
so it was not somebody
No.
sending out
No,
code,
no,
nothing.
no, nothing. It happened right in the orbiter. And we had the benefit of gaining a lot of knowledge with the CY2 craft, which imaged, right? Those are the images which we used for CY3. So the job was easier.
So, I mean, a lot of people said CY2 was a failure, and
No, it was not. It was not. Yeah. Orbiter gave us a lot of data.
changing the reducing the velocity and making it into something in orbit is itself a very big task.
Yeah, but that rotation won't consume so much energy as your main orbital correction. Turning won't consume much energy.
That's why they say it is 95%, sir.
Yeah, percentage you can up to you how much you can attribute, but but the orbiter was a complete success, right? How much you percentage you attribute to orbiter is up to you. It's subjective, yes. Any other questions?
Outside. Outside. WBP is saturated 3.5 days prior to the sunset one.
Uh, what is this 3.5 days coming in here?
And window for the planet's nearest side, that is planet. It should be 3.5 days prior to the sunset point. One has to land on the dark side, far side.
Oh, far side and dark side are different. First of all, yeah, far side also gets light, right? Far side always gets light. So that also has a lunar day and lunar night. So it's communication, yes.
Chinese movies of orbiter. I like the orbiter. Yeah. There has to be some craft. Something like the geostation demonstrate that something has to be decided. And give us some light.
Any other questions?
no, no questions online. There's a lot of the same positive, awesome, nice topic, Shankar.
All right. So it's a long journey, even though there is a lot to internalize. But then I believe that we have moved from the schematic world into more textured, layered knowledge. Right. I hope that knowledge has increased. But beyond that, it's a matter of pride. It's a sense of achievement which you have done, right? And it's a that is when you have to reflect beyond orbit, beyond physics, everything, correct? And this picture is worthless, right? Amazing. So I will leave it at that note, with Carl Sagan's note on the red dot. Okay. Thanks, everyone.
Control item.
Sure.
Also obvious passion.
Maybe I feel not
Thank you, everyone. Shankar. It's a very, very good talk. I mean, I'm sure I learned a lot. There's so many gray areas that I had. several of those areas they got covered. I learned quite a few things. Uh, Doing this on a Sunday afternoon, typically we tend to take it easy on a Sunday. Really nice of him to come down all the way and give his talk. Really appreciate it. As a mark of token of appreciation, we'd like to give a small memento to Shankar.
Great. Thank you. Thank you. Thank you. And
Thank you very much.
thank you.
Oh, please.
Sure.
Rush, and balance.
Thank you. Thank you. We'll end the session. Uh, ah, doing your cinematography trick.
Okay, so we'll end the broadcast now.
We'll end the broadcast. All right. Thanks everyone for joining.